Hello everyone. In previous lessons, we were working on estimating a population proportion, and today I'll introduce you to estimating a population mean. To begin, we start by choosing a simple random sample of size n from a population that has a known mean mu and a known standard deviation. As long as the distribution of the population is normal and independent conditions are met, then we use this formula here to calculate the confidence interval. One of the problems, though, is that notice we don't know the population mean. That's why we're estimating it. But to use this formula, we need to know the population standard deviation. If we knew the population standard deviation, wouldn't we know the population mean? So this is a bit of an unrealistic situation. Luckily, there's an alternative that can be used called the t-distribution, and the good news is that it also works with small sample sizes, as long as there's no extreme skewness or outliers. Let's take a look at how this works. Here we have the t-distribution and the standard normal distribution. The standard normal distribution is in purple, and the t-distribution, there's one here in red and one here in blue, and you might be wondering why they are different, and that's because they're based on different sample sizes. The red dotted line has what's called 2 degrees of freedom, and the blue line has 9 degrees of freedom. Notice a few things about the t-distribution. The density curve of the t-distribution is similar in shape to the standard normal distribution, mound-shaped, symmetric, centered at 0. But notice that the spread of a t-distribution is a little bit greater. The tails here are a little bit higher, and the center of the distribution is a little bit lower. And this last item that's listed here might not be so apparent, so we'll go to Fathom in a moment. It says, as the degrees of freedom increase, the density curve approaches the standard normal curve ever more closely. Let's take a look at this in Fathom. So here I've got in Fathom this green curve, that's our normal distribution, and then we have this blue curve, which is a t-distribution. Notice that if I actually wanted to see more of this t-distribution, we might actually have to go out 6 standard deviations to get almost all of the t-distribution under the curve. Right now I have 3 degrees of freedom, and I'm going to use a slider to increase the degrees of freedom. And notice as I increase the degrees of freedom, the t-distribution gets taller in the center and gets pushed down on the ends until eventually it almost looks like a normal distribution. And when do you think that's going to happen? If you said 30, you're on the right track, because 30 was the number that we said we needed to sample in order to have our sampling distribution be approximately normal. And when we're at 30, you can barely see the blue curve here behind the green curve. So at 30 degrees of freedom, or actually 31 is even better, that's based on a sample size of 30. When we have a sample size of 30, we know that the t-distribution is almost the same as the normal distribution. So like a z-score, a t-score tells us how far the sample mean is from the population mean in terms of standard deviations, so that works the same way. And as I started to mention a little bit earlier, we calculate degrees of freedom by using sample size minus 1. It's the easiest formula you'll have in stat. So let's take a look at how we get the critical values, or the t-star values. Suppose you wanted to construct a 90% confidence interval for a population mean of a normal population based on a simple random sample size 10. What critical t-value would you use? So let's go to the t-table that's in our books. And so we're doing a 90% confidence interval, which means I am 5 columns from the left, and our sample size was 10. That means I need 9 degrees of freedom. So I'll come over here, 9 degrees of freedom, and I said 5 columns over, so we have 1.833. Notice that that's quite a bit different than if we had a 90% confidence interval for a population proportion, 1.833 versus 1.645. So our interval is going to be wider because we would expect to see a higher standard deviation and more variation when we have a smaller sample size. So let's take a look at that. Degrees of freedom is 9. and from the table we get the t-star value of 1.833. Could we also get this value from our calculator? Well, of course we could. We can do something called inverse t on the calculator, and the area to the left of the t value is 0.05, and you might be wondering why it's 0.05. Well, that's because if we're talking about a t distribution, and excuse the crudeness of my drawing here, 90% will be contained within our negative t star and positive t star values, which means I have 10% left over between my tails. And so if I have 10% left over split equally between the tails, that means I would have 5% in each tail. So I can either look up 0.05, or I could look up 0.95, which would be the area to the left of the positive t star value. This would be 0.95. So let's take a look at how we could do this on our calculator. So we go to second vars and choose option 4, inverse t. The area to the left of our t star value is 0.05. The degrees of freedom is 9. We come down here to paste, hit enter, and notice this gives us the same value as we found on the table. So let's actually take a look at constructing a confidence interval. Just like we had conditions that we need to check for working with a population proportion, we have conditions that we need to check for working with a population mean. The random condition, normally we're taking from a population, and so we'd want to do random sampling, but notice we could also have a randomized experiment. So we're looking for either a random sample or a randomized experiment. The population has a normal distribution or the sample size is large. This is exactly what we were talking about when we were talking about the sampling distribution for a sample mean. And we'll talk more about how to check this if our sample size is not large. Is there a way for us to know if this is true or not, even if we don't have that information given to us? And then that independent, the way we check that is that with that 10% condition. We want to make sure that we sampled no more than 10% of the population size. And once again, our formula or our recipe for calculating a confidence interval is our sample statistic. In this case, it's x bar plus or minus our critical value. That's our t star value. And then the way we calculate the standard deviation of the statistic, or sometimes referred to as a standard error, is to take the sample standard deviation, since we don't have the population standard deviation, and divide by the square of the sample size. We've seen this before as well. So let's work our way through an example. So in this example, as part of their final project in AP Statistics, these two girls randomly selected 18 rolls of generic brand toilet paper to measure how well the brand could absorb water. And they poured a quarter cup of water onto a hard surface and counted how many squares it took to completely absorb the water. And here are the results from their 18 rolls. We're going to construct a 95% confidence interval for the mean number of squares needed to absorb a quarter cup of water for this particular brand of toilet paper. So let's check to see if our conditions are met. The random condition, it says random selection. The 10% condition seems reasonable. It's safe to assume that over 180 rolls exist. We've sampled no more than 10% of the population. And then normality, if n is less than 30, and it's less than 30 here, we either need to know that the population distribution is normal, which we don't know about this population, or we need to take a look at a normal probability plot or a histogram or dot plot to see if normality is reasonable. So let's actually do that on our calculators. I've already entered these values in list 1 on my calculator. You might want to pause the video and enter them into list 1 yourself. But you can see I've already entered them into list 1. And now we're going to do a stat plot. And plot 1's on here. I'm going to do a normal probability plot. Although, as I said, we could do a histogram if we wanted to. With a normal probability plot, we're looking to see if the distribution is approximately linear, or the graph is linear, I should say. So zoom option 9 is zoom stat. That appears fairly linear. Let's take a look at the histogram while we're here. And once again, zoom 9. Actually, let me go back there. I think I said that the frequency was in list 2, and the frequency is just 1. Zoom 9. Oh, let's try that one last time. I guess I have to put in frequency of 1 down here. It doesn't like it otherwise. There we go. So it seems like normality is reasonable. Just a normal probability plot would have sufficed. You actually didn't need to also do the histogram. So let's go back to the problem and notice that I've made a note here that says normality is reasonable because the normal probability plot is fairly linear. So make sure you say that. Just don't say normality, check. You need to talk about how a normal probability plot or a histogram shows you that normality is a reasonable assumption. So now we're ready to actually construct our confidence interval. And this is how we construct our confidence interval. Our sample mean plus or minus t star times the standard deviation of the sample divided by the square root of the sample size. Our sample size was 18. And to get the sample mean and sample standard deviation, once again, I used my calculator. I did stat calc, one variable statistics, and we can leave the frequency list blank. Notice our calculator gives us our sample mean and our sample standard deviation along with our sample size of 18. So we can plug those values into our formula. Sample mean, sample standard deviation, sample size, and then how do we get this t-star value? Once again, we'll need to use the table, the t-table, with 17 degrees of freedom. Since our sample size is 18, our degrees of freedom is 18 minus 1, or 17. And we're going to be constructing a 95% confidence interval. So 95% confidence, 17 degrees of freedom. Let's go to the table. So here's 95% confidence, 17 degrees of freedom means we're at 2.11. And I know that was a little hard to see. Let me make that larger. 95% confidence, 17 degrees of freedom is right here, 2.11. All right, so here's our confidence interval stated as the sample statistic plus or minus our margin of error. And we're now going to interpret this confidence interval. We would say we are 95% confident that the interval from 23.52 to 26.36 contains a true mean number of squares needed to absorb a quarter cup of water for this brand of toilet paper. However, we need to be careful because a t-distribution will not be accurate if there's strong skewness or outliers in the original population distribution. And we'll be talking about this either on Wednesday or Thursday of this week. Once again, just like we could use our calculator to do a one proportion z interval and get our confidence interval for our proportion, we could actually get this interval from our calculator. So let me show you how to do that. So we go to stat, over to tests, and notice we have some tests here. That's hypothesis testing. We'll be learning about that in the next chapter. But we're going to come down here to t-interval. And notice I have the option of using the data that's already in my calculator, which is in list 1, or if I didn't have the raw data, I could come in here and enter the statistics. Let's say data. The frequency is 1 because each value is entered in list 1 exactly once. And I'm going to say calculate. Notice that this is the same confidence interval that we got when we did the calculation by hand, 23.523 and 26.366. So I know that this might be a little bit confusing, but we're going to spend a couple days on this. And actually, I think the formula is easier to work with than the formula for one proportion z intervals, with the exception of having to look up the t-star value. We'll be sure to go over any questions that you have on the 8.2 homework tomorrow before your quiz on 8.1 and 8.2.